Okay, this is lecture 3, gears. So the main function of gears is to change ratios such as speed and torque, and to change direction of rotation. This is done by using the gear ratio, which we usually are going to calculate using the number of teeth of gear 1 over the number of teeth of gear 2, or vice versa, depending on what exactly we're trying to calculate. For example, if we're doing a speed change and we're going from a big gear to a smaller gear, such as, let's say we had a gear where gear 1 had 16 teeth and gear 2 had 32 teeth. So in this case, our M1 over M2 would be 1/2 for the speed would be multiplied by 1/2. If we had input speed of 500 RPM, it would go to 250 RPM for gear 2. But if for torque, it would be the opposite, so then it would equal 2, and our torque would double in that case. And one of the main problems we've run across while designing gears is interference. And interference happens when two gears are touching, but it's not in conjugate. So normally you want your gears to look like this. Something like that. This gear, and you're gonna want the other gear to be in here, like that. But when their interference happens, you usually have contact such as that instead of down at the bottom here. Contact at this point. And to eliminate when trying to eliminate interference in gears, we're going to need to use pressure angle tables to determine minimum number for the pinion gear and what our maximum number can be for our driven gear. And we once again we'll be using our gear ratio to determine the minimum pinion gear stuff. Let's say if we have, I think, 3 as our ratio, this is equal to 3, then our minimum pinion gear has to be 16 and our max can be like 112. So let's put this stuff into action and let's design a gear. So let's say we wanted to reduce speed from 4,500 RPM to 100 RPM. And we wanted to do this with the minimum number of teeth, and we don't want interference, and we want also the gears, 2 shafts to be in line. So we're going to have an input shaft here, some gear, some other gear, let's say, output shaft, gear, and that should line up perfectly. Doesn't this wrong, but it will. And then we're also going to have a pressure angle, because we need to use our tables to determine, so we have no interference, of 20 degrees. So that's the requirements. So to begin, we're first going to want to know what our E value is. So that's the ratio of how pretty much far we got to drop here, which is going to be the low over the fast, which would be 100 RPM for the low, 4,500 for the fast. So 1 over 45 is our E value, which number for the low side, number of teeth for the low side, number of teeth for the fast side. And we're going to want to break this up a little bit farther into, we're going to break this number down in the 1/9 5. And the reason we did this is because we have two different sets of the gears, as I showed earlier in the drawing. And so one is going to have 1/9 ratio, the other is going to be 1/5 ratio. So we'll do that. We'll do the input to be 1/9, and the right side of the shaft to be 1/5. And then we also know that since we want the sizes to be the same, the shaft sizes, we're going to have N2 plus N3 equal N4 over N plus N5. Because otherwise the shafts would be off, and that makes it more complicated to design a square box, or boxes to be bigger. So now we're going to go into using our equations. We have 3 equations, 4 unknowns, but we can just plug in for one side something that fits into this ratio. And so since we have 1/9, why not just use 1 and 9? So we have N2 equals 1, N3 equals 9. So then we plug that back into the equations related with shafts, and we get 10 equals N4 plus N5. So now we have 2 equations, 2 unknowns. So we're going to solve this upper equation and plug it back in here. So we're going to get multiply N5 over here. So we have N5 over 5, multiply 5. We get 5N4 equals N5. And then we plug that back in here. So we get 10 equals 6 N5. So N5 is equal to 10 over 6 or 5 over 3. Okay, so now we gotta figure out where I want to write this. So this is keeping N2 equals 1, 3 equals 9, and 4 we don't know yet, and 5 is 5 over 3. So now we work back, plug 5 over 3 back into this equation. So 10 equals N over 4 plus 5 over 3. So we get N4 is equal, subtract that, and it will equal 25 over 3. Okay, so now we have the gear sizes. If we didn't have to do anything with interference or anything, we could just plug this in and it'd be good. But since we don't want any interference, we're going to have to go back at the tables and look at our ratios. And we're going to, let's say we're multiplying this out by 12, because we have the 3 here, least common denominator. Then we get 12, 100 and, I don't know, 8, and then 2 other large numbers, and that would be too small. So we go up to 18, which will be the next least common factor, and we get that N2 equals 18, and 3 equals 162, and 4 equals 30, and N5 equals 150. So if we go and look at the interference tables for a 20-degree pinion gear or pressure angle, we see that we're meeting the minimum of 18, or we can meet the minimum, and we're under the max, which is going to be insanely high, because I think for N17 it's 1,000 something, so for N18 it's got to be like 10,000 something. And there we go. We're gonna plug this in. Then we would have so we're reducing speed. So we have our 18 tooth gear here. Then we have our 162 tooth gear here to another small 30 tooth gear. And a 150 tooth gear. And shafts would be in line. So what is that? 5. And there we go. That is it. We have designed a gear train. We talked about everything. There we go.